Hello and welcome. Today we're going to discuss the application of polynomials to a very practical purpose. And this is the calculation of magnetic properties for different materials. Magnetic materials are very important for a wide range of engineering applications, especially for power conversion. If we want to build an electronic circuit that converts one type of electrical power into another, we often have to use magnetic materials to do so. And our choice of magnetic materials are often constrained by the operating parameters that the circuit must function under. So I want to give you an example of how a polynomial math actually applies to this very practical problem. So we're taking a look at a technical bulletin published by the Magnetics company. And as the name would imply, they manufacture magnetic materials. And there are certain properties of these materials that are very important for electric power conversion. So we're going to skip ahead to page 5 here and take a look at a graph that's included in this document. And the graph I'm referring to is the one on the left-hand side here. Normalized power loss as a function of temperature. So what this means is when you are using magnetic materials to help convert electrical energy from one format to another, there's going to be a certain amount of power loss, a certain amount of energy that is converted to heat that we don't want. In any sort of power conversion process, we want it to remain as efficient as possible and have the least amount of our energy being converted into heat, because that's generally considered waste. So to optimize the design of our power conversion circuit, we need to make sure that we're operating in a range that the magnetic material is not going to waste too much power. Or if it does waste power, that we have a firm grasp on how much is going to be wasted. So this particular graph shows us for one of the types of materials this company manufactures that they call F material. They have a solid curve that's shown here that plots how much power loss that magnetic material experiences as a function of ambient temperature. So if we're operating at 20 degrees Celsius, which is roughly what we call room temperature, we expect this to be at a normalized power loss of 1, meaning that's our baseline for comparison. As the temperature begins to rise and as it begins to fall, the magnetic material becomes less efficient for this purpose, and we end up wasting more power. It's important to understand exactly how much is being wasted or distributed in this manner in order that we can design the most efficient and reliable power conversion circuits. So someone took the time of actually testing a sample of this F material for its power loss over a wide range of temperatures. The data they collected became the points that make up that solid curve. Okay, so what do we do with this information? Well, if we're going to be designing a circuit, if you're, for example, an electrical engineer who's designing a circuit that's going to be doing this power conversion, you would probably be using a computer to mathematically model this material's properties. So you need the computer to be able to replicate this curve somehow. Well, how do we do that? One effective way of doing that is by using a mathematical technique called polynomial regression that takes a set of data points like this and tries to figure out a polynomial equation that approximates the shape of that curve. And that is what you see with the dashed curve here. You can see the dashed curve very closely follows the solid curve here, but then it begins to diverge a little bit. Then it meets it again, diverges a bit, meets again, etc. The order or degree of the polynomial, the higher that number is, the more terms in the polynomial, and the more closely, in general, that equation is able to fit the collected data. And when we're done with it, the upshot is that we will have an equation that's a very close approximation of describing what this material actually does, based on real empirical measured data. So the polynomial coefficients vary with the material. And if we go to the page right above this, you find a table, power loss versus temperature. And for the material we were looking at before, the F-type material, it gives different coefficients that are going to go into this polynomial equation. Here is the equation right here. The normalized power loss is equal to A plus BT plus CT squared plus DT cubed plus ET to the 4th power, where T is the temperature of operation, and the A, B, C, D, and E are these different coefficient values. And as I said before, for each type of material, there's a different set of coefficient values. So what we're going to use right now is Python, which is a computer programming language, to create this polynomial formula for the type F material. Then when we're done with this, we will do some simulations where we entered in different values for temperature and see how closely it replicates the data on the graph that we saw on the other page down here. So here we go. I'm going to open a Python console, and this is going to allow me to enter in data and then also evaluate the equations. So what I'm going to do here, since we're interested in simulating the F-type material, I'm going to be entering in the values for these coefficients. A is equal to 1.44. I'm simply creating variables in the Python language and assigning numerical values to those variables. Next, we have B is equal to negative 2.61 times 10 to the negative second power. An easy way to represent this in computer programming is with the E letter followed by the power of 10. So negative 2.61 E minus 2 is just another way of saying negative 2.61 times 10 to the negative second power. By the way, most hand calculators also have an E or a double E button. Generally, it's a capital E to distinguish it from Euler's constant, and it does the same thing. But in computer programming, it accepts the lowercase e just as well. So for C, I'm going to enter this value right here, 4.51 times 10 to the minus fourth. So 4.51 e to the minus 4. My D coefficient is 1.82 times e to the minus 6. My E coefficient is negative 2.65 times 10 to the negative 8 power. So those are my coefficients. And I can clear my screen here and just review them just to make sure I've got them all correct. 1.44, negative 0.0261. C is 0.000451, that looks right. D is 1.82 times 10 to the minus 6. And E is negative 2.65 times 10 to the minus 8th. Great. So I've got my 5 coefficients programmed in. Now what I'm going to do is actually enter this equation as we see down here. So what I'm going to do is simply go A, don't want capital, A plus B times T. And before I do that, I should actually define a value for T. Let's set a temperature of 20 degrees Celsius. Now I'll enter the equation with T in it, and we'll see what the result is for power. So A plus B times T plus C times T squared plus D times T to the third power plus E times T to the fourth power. And when we enter that with the value of T that we gave Python right here, T of 20, it tells us the power loss is 1.1087. Okay, well, let's scroll down here and see how that matches our curve. I'll shorten my Python window like this. Doesn't have to be quite as wide. So what we're saying here is that at 20 degrees Celsius, the measured or empirical data put our normalized power loss at a value of 1, and the curve that is fit to try to match this empirical data actually puts a power loss a little bit higher. Now it's hard for me to read exactly how high that is. I can tell it's way less than 1.5. It's even less than 1.25. I think 1.1 sounds about right. So that figure right there, 1.1, looks about right when I compare that to the graph. So far so good. All we're doing is we're proving that this equation here is indeed following the dashed curve that's shown on this, and at the same time is approximating the solid curve, which is based on real measured data. So let's try a different data point. Let's go over here and try a temperature, let's say, of 60 degrees Celsius. And then I can recall the equation, run it again. So we get 1.54728. Okay, so let's take a look at 60 degrees Celsius here, and that ought to be roughly 1.5. And there we go, 1.5. There we see it. So far our equation is actually matching the curve. Let's pick another point somewhere on this graph that would be easy to test. I see what looks like a pretty easy point right here. Easy, I say, because it falls very close to the intersection of one of the horizontal vertical lines. So if we're looking at minus 40 degrees Celsius we should see a power loss of roughly 3. So coming over here to Python again, I will enter a temperature here of -40, rerun the equation, and we're getting a power loss of about 3. Okay, so what's the significance of this? Well, we have an equation with a set of coefficients programmed into the computer that's able to fairly closely emulate the real-life magnetic behavior of this material. With this equation, we could plug it into any number of different computer simulations and be able to test in simulation the performance of our power converter circuit based on real-life measured data. So the polynomial equation becomes the bridge, so to speak, between the researchers' empirically collected data and our computer model. It's not perfect, and you can see that because the dashed curve does not match the solid curve perfectly, but if it's close enough, then it's good enough for our simulation. And we can use our computer simulation to design the circuit in a rough sense, and then we will build a prototype, actually test that prototype, and see how well it works. Practical applications. Why would we care about the power loss of this converter circuit? Well, one application is simply energy efficiency. If you are using this power converter circuit to convert energy from a battery to run something like a laptop or a cell phone, you're interested in getting as much runtime as possible out of that battery's life. And key to doing that is making sure you don't waste any of that battery's energy. And by wasting, I mean dissipating in the form of heat, where it doesn't do the computer or the cell phone any good. So keeping that power loss at a minimum is ideal. Also, let's say you're designing a power converter circuit that has to operate in a non-ideal environment. Let's say one that's not at room temperature, one that's operating really hot or really cold. Perhaps this power converter circuit is going on a space probe where it can get extremely cold and extremely hot. Or maybe it's used for some sort of geological data gathering system where it has to be buried in the earth, operating at a high temperature. You need to know at those elevated temperatures or very cold temperatures how well this device will perform and if the power loss is going to cause other problems that you don't want. So having a mathematical model of how that circuit might perform is a very valuable thing.